This is the video walkthrough for Physics 2212 Lab 1 on charge tapes. The overall goal of this experiment is to determine the approximate excess charge on a single piece of Scotch tape. Our method to go about doing this is to first find the sign of the charge on a piece of Scotch tape by comparing it to an item with a known sign charge. To do this, we use the pen test, where you find the charge of a pen by rubbing it on hair or a piece of cloth or some other material that would give it a negative charge. And from there, we can use that known negative charge to find the charge on a piece of Scotch tape by finding whether it repels or attracts to this pen. After doing this, we then measure the magnitude of the repulsion forces between the two pieces of tape by balancing them with the gravitational force when they are hovering or levitating with each other. Some underlying assumptions that we need to take into account before completing this lab is to treat the long tape as though it were a point charge with all of the charge concentrated at the center of the tape, as well as assuming that each U-tape made has about the same amount of charge, which is evenly distributed along the length of the tape. Some important laws and formulas that were used in our calculations throughout this lab is Coulomb's law, which states that like charges repel each other while opposites attract, as well as Newton's second law, F equals ma, which is useful in finding the force between the two pieces of tape because you can use the tape's mass as well as the acceleration due to gravity to find the gravitational force. And from there, we know that because the pieces of tape are hovering in air, that the force due to gravity is going to be equal to the force due to the electric field between the two pieces of tape. Some other formulas that we used throughout this experiment is the formula that the force equals the charge on the piece of tape times the times the magnitude of the electric field, as well as force equals Coulomb's constant times the two charges of each pieces of tape divided by the squared distance between the two pieces of tape when they're in equilibrium hovering. Experimental setup: the length of my tape from my sample was 0.2 meters or 20 centimeters, which means the mass was 0.0002 kilograms. The distance found in equilibrium between the two floating pieces of tape were 0.0025 meters or 0.25 centimeters. From there, we used Newton's second law, as stated in the previous slide, to find the force due to gravity to be negative 0.001962 newtons. And because we know that the force due to gravity is equal to the force due to the electric field when in equilibrium, we know that the force of the electric field between these two pieces of tape is positive 0.001962 newtons. Some more calculations after this is to modify the equation to find the charge on a single piece of tape. So we manipulate one of our equations from the previous slide, or from one of the previous slides, to find the charge on the piece of tape to be 1.167 times 10 to the negative ninth coulombs. We then take this number to find the number of deficient electrons, which is the previous number divided by the number of atoms in an electron, to find 7.295 times 10 to the ninth. To find the total number of the atoms on a piece of tape, you divide the tape surface area divided by the atom surface area. And from there, we can find the percentage of electrons lost, which is 1.92 times 10 to the negative 6% of electrons on the piece of tape. Here is some screenshots of my GlowScript code that essentially goes through the same calculations that were just walked through on the previous pages, and to see the accuracy between each method. And with the model output that came from my script, we can see that all of the calculations shown at the bottom of this model here are very closely related to the hand calculations that were completed in previous slides, such as the charge tape being 1.16 times 10 to the negative ninth coulombs, and the number of electrons lost, and the percentage of electrons lost, of deficient electrons from the piece of tape. This model also shows the two the two forces due to gravity and the electric field and how they are balanced in equilibrium, with the yellow ball in the middle representing one of the pieces of tape hovering. The downward facing arrow is obviously the force due to gravity, and the equal magnitude arrow pointing upwards is the electric force due to gravity, or electrical force of the piece of tape. Some additional questions are, what if electrons had a positive charge and the protons had a negative charge, and what would change about the observations made? The observations made would be the same. The signs related to the pen from the pen test and the pieces of tape would be flipped, but the observations would be the same because everything would be flipped and everything that previously repelled would still repel, and everything that previously attracted would still attract. And why is it important to handle the charged tapes as little as possible, and what would happen when it comes into contact with your hands or other objects? You would like to limit the transfer of charged particles as much as possible, to limit the transfer of charged particles between your hands and the pieces of tape to keep the accuracy of the amount of charge on the piece of tape without messing it up. Thank you for listening to my lab walkthrough.